I hope you have your notebook and pen ready because it's time for another lesson with Professor Brooks. This time we're going to talk about what happens to molecules when they dissolve in water. So the learning objective is to be able to draw and describe at the molecular level, so the microscopic domain, pictures of compounds that have dissolved in water. You'll then learn to distinguish between strong electrolytes, weak electrolytes, and non-electrolytes. So all matter is made up of multiple molecules, and those molecules are all interacting with each other. We talked about this when we were looking at states of matter. When matter encounters another substance, like water, there's a new opportunity for interactions. So when a solid enters into liquid water, the individual molecules along the surface of that solid are having a challenge between the interactions they're having with their near neighbors and the new interactions they're having with the water molecules. If the attraction between the solvent, the water in this case, is stronger than the attraction to the near neighbors of the solid, then that solute is going to dissolve. One of the things that contributes to the high solvent characteristics of water, the ability of water to dissolve many ionic solids, is that water is a polar molecule. And we'll learn more about what this word means later in the semester, but for now I just want you to know that within a molecule of water, there is an unequal distribution of the electrons in the molecule overall. It turns out that most of the electrons in the molecule are pulled towards the oxygen atom, meaning that the hydrogen atoms are slightly depleted. So looking at our representations of water, you can see the structural formula here. And then the space-filling model is what we're going to see in the coming slides. So I just wanted to remind you about how with the space-filling model, we use red for oxygen and white for hydrogen. And what you're looking at on the right is a new representation called the molecular electrostatic potential. And this is a way of using color to describe where the electrons are abundant or depleted. And so we see a red region around our oxygen atom, meaning a high electron density. That is also denoted by the lowercase Greek delta, meaning a slight amount, and then the negative symbol for negative charge. On the right-hand side of the water molecule, you see all this blue coloration around the hydrogen atoms, meaning that there is a low abundance of electrons, and we see that denoted with delta plus. Here we see an illustration of what happens when polar water molecules encounter an ionic solid. You can see here that the slight negative charge on this water molecule is being attracted to the positive charge on the ionic solid. Now, normally we would say that that positive charge is already being balanced out by its surrounding anions. However, once that water starts interacting with the cation, the positive ion, it weakens those interactions and more water molecules can come in, so that we end up with the net result of multiple water molecules all pointing their slight negative charged ends towards that cation. And that gives the energy necessary to pull that positively charged ion away from the surface of the ionic solid. Down below, we see the opposite interaction happening, where the positive end of the water molecule, next to the hydrogens, is being attracted to the anion, the negatively charged ion. This is what we mean when we say that ionic solids dissociate in water, in that the cation and anion completely separate and are independent species. Now I'm going to contrast that with what happens when we have a polar molecule dissolving in water. Now, if we think about the first case as being something like sodium chloride, you can take a teaspoon of salt, put it in water, and it dissolves. That's an ionic solid, and it would look just like the previous representation. But you can also take a teaspoon of sugar and dissolve that in water. But sugar is not an ionic compound. Sugar is made up of a molecule called sucrose, and it is a molecular compound. What we're looking at here on the left is a space-filling model representing a cube of sugar. Sugar molecules, or sucrose molecules, are also polar, just like water, meaning there are parts of that molecule that are slightly more negative and parts that are slightly more positive. So our water is still going to be interacting with the sucrose along the surface. And it will be able to abstract a single molecule away from the solid by surrounding it with multiple water molecules. And in the end, we will have individual molecules of sucrose completely surrounded by water. So what we're seeing when a polar solid dissolves, the molecules remain completely intact, but they become independent from the array that they were in the solid. This leads us to our learning objective about the word electrolyte. So an electrolyte is a substance that when dissolved in water can conduct an electric current. This means that when they are dissolved in the water, they must be producing ions because water alone does not conduct electricity. Strong electrolytes are molecules that dissociate completely. So we're talking about ionic compounds when we're talking about electrolytes, and they may dissociate completely, meaning every single molecule separates into its component cation and anion. Or if we're dealing with a weak electrolyte, only some of the ionic compound will actually dissociate. All of it may dissolve, but only part of it will dissociate into its contributing ions. Non-electrolytes are substances that don't produce ions at all, like our sugar example earlier. So looking at these images down below, we have a pictorial view of the difference between a strong electrolyte and a weak electrolyte. It's a little bit more cartoony than our previous examples, but just to show you, this little blue blobby thing is meant to represent a water, and then the plus signs on the red indicate the cation, and the negative signs on the green indicate the anion. As you can see in the image on the left, every red positive is surrounded by water and is not at all touching any of the green negatives. So the image on the left would be considered a strong electrolyte. Every ion has dissociated. Now comparing that with the image on the right, we can see individual cations surrounded by water and an anion surrounded by water. But we also see paired formula units. So this is representing some molecules of this ionic solid that have been dispersed within water, but the individual ions have not separated. That's what we mean when we say a weak electrolyte. We can test a particular solute to determine its conductivity by dissolving it in some water and then placing a light bulb with the two ends of its wires separated into that solution. So in a conductivity test like illustrated here, the only way electricity can flow out of the wall and into the light bulb is if there are some sort of ions between the anode and the cathode of our circuit here. So here's an example of a non-electrolyte, ethanol. It is a molecular compound. It does not dissociate into ions at all, and so we do not see our light bulb glowing. We have no conductivity. Strong contrast to that, the next example is potassium chloride. That is an ionic solid and it dissociates completely, and so we see the light bulb at its brightest. On the right-hand side, we're seeing the example of a weak electrolyte, acetic acid. So this is the acid that is part of vinegar. And acetic acid, when it dissolves, will only dissolve partially. So we see there are some ions in there, but there's also intact molecules. So our light bulb does light up, but not as brightly as with our strong electrolyte. All right, so if we've been paying close attention to this video, you should be ready for this conceptual checkup. So we have 3 images below. Take a moment, look at them, and see which one represents the strong electrolyte, which is the weak electrolyte, and which is the non-electrolyte. And then just keep calm and study on.